Hello and welcome to the Linearizing Graphs video tutorial. Here we're going to look at how to linearize a graph and why we're going to linearize a graph in the first place. So in our example here, we have these data points for time and position, and they've already been placed. And here they are, and it's pretty clear this is an exponential graph. So what we're looking at is we're looking at y is equal to, well, mx plus b would be a linear graph, but this is an exponential graph. So we're looking at squared. So to create this model, what we're going to do is replace y with whatever y is, so that's position, in meters, equal to whatever m is. We'll get back to that. X squared, x is time, and that's in seconds, and square that, plus b. And it looks like b is going to go down to 0, so it looks like the y-intercept is 0. We'll figure out later what that's going to be. The problem we come across here is, well, what is the slope? Well, we can go to our graph and linear fit, and it will give us the slope, but this isn't a linear line, so this makes no sense. We're taking a linear fit of nothing essentially, so we really can't do this. So we need to find a way to make this linear. Well, because this is a exponential graph, if we square these down here, the x values, it should make this linear. The way to think about it is these values here are squared values of these values times some constant that we don't know. If they were exactly squares of these numbers, then that constant would be 1. So why don't we just take these numbers and square them? So let's see here. We got 0.5 squared. This is going to take a little bit of time. 0.25. 1.3 squared is, 1.3 squared is 1.69. 1.9 squared is 3.61. And just going to keep doing this on the calculator. I know what that is. That's 36. 6.2. 8.7 squared, 75.69. You can see the dots here changing. This is becoming linear. 11.1 squared, 123.21, 16.5, 272.25, 21 squared. It's going to be just over 400, 441. So here's our new dots, and look at that. That looks really linear. So I'm going to linearize that. And there you have it. And now we actually do have a slope. This is our slope right here, 1.7. However, we have to take note that this is actually not time anymore. We took all of our time values and squared them. So I'm going to go into here, and I'm going to change this to time squared, because that's what it is. It's time squared, which means this is t squared. And the units are seconds squared. And the reason why I'm doing that is because now I have my units for slope right here with the second squared. This is meters is the rise, and time squared is now the run. So bring back this text box. So I'm really looking at position. This slope right here that I did not know before is 1.7 with the units of meters over seconds squared. Time, now I can go time squared seconds squared, or I can just parentheses the whole thing and square it. And my y-intercept is going to be, this is basically 0. This means times 10 to the negative 14th. It's an incredibly small number, so 0 meters. And there you go. There's my linearized graph for what was a parabola to start. I have one more example here to show you. So here's another graph, and this one looks like it is going to be inverse. So we'll curve fit this to an inverse So there's inverse right there. Go down a little bit and try fit. Fits perfect. And take note of this number right here, 5. So we'll be coming back to that. And okay, and look, that's a perfect fit. So we're going to go ahead and here's a text box, and it's gone, and it's back. And if it was linear, it'd be y equals mx plus b. But is not linear, it's an inverse function. So we're looking at y equals, I'll do it up here. It's y equals m times 1 over x plus b. So my y is going to be position. And again, we're stuck without an m value for this, what essentially looks like a linear function. If we can do y equals m, all of this is x plus b. So our x value is times, so let's just do 1 over these values here. So remember this number, remember the number 5. So let's see, gotta do it again the long way. So 1 over 0.2 is that, 1 over 1 is 1, 1 over 3 is 0.33, 1 over 6, 0.167. You can see the dots moving into a linear shape right here. 0.11, 0.083. I'm just doing 15, then hitting the inverse key on the calculator. 0.067, so I'll hit 18, inverse key, 0.056. The inverse key looks like a little 1 over x on the calculator I am using. 0.048, and 1 over 24 is 0.0417. Alright, so here are, I'm going to get rid of this because this doesn't apply anymore. This has been changing to reflect these dots as an inverse function, which they're not. So instead, I have these new dots here, and I'm going to linearly fit those. And look at that, I get a slope of 5. That is not a coincidence. So I actually did have the slope before. It was the a value in the previous box here. So this isn't time anymore. This is 1 over time, which means this is 1 over t, which makes this 1 over seconds. Done. So basically, I have the exact same graph as before, but now set as a linear function. So position is equal to 5 meters over 1 over seconds. I'm stealing that unit from right there. That I can do that because I set these to be correct. Times time, and whoops, that's not true. 1 over time, and that's in units of 1 over seconds, plus b. It looks like our b value is again basically 0 meters. Thank you for watching the Linearizing Graphs video tutorial.